Fluid simulations have been a long-time headache for engineers. You probably wouldn't think that something as simple as water pouring out of a glass would be such a nightmare to simulate accurately, but it is, and engineers have to deal with scenarios far more complex than that. For instance, chemical engineers have to model how fluid mixes inside of a reactor, how liquid moves across a distillation tray, or how a spill might spread through a containment area. All of that runs on the same difficult physics around fluid mechanics. Now, the fluid simulation problem isn't just an engineering problem. It spills over into other industries entirely, VFX being an obvious one. Creating realistic CGI water is key to a lot of major film sequences. If it doesn't look or feel right, it ruins the immersions. Video games are another. These three worlds, engineering, VFX, and video games, all deal with the challenge of fluid simulation, but with completely different approaches to suit completely different needs. VFX artists don't need exactly a one-to-one simulation, as that would be a bit overkill. They just need it close enough to be realistic that it's convincing. But even just that is extremely difficult to achieve. To make realistic looking fluids, your fluids would have to move and look realistic. These fluid simulations are incredibly complex and need a lot of computational power to run. The reason behind their complexion is because there's a set of equations that governs how a fluid moves at every instant. Now, that causes some issues for video games. For VFX, those calculations can be pre-baked. If it takes a couple of days to render out a scene with complicated water, that's fine. The calculation only has to be done once, and then if the artists are happy with how the simulation is, they can move on to working on other aspects of the scene. Blender's built-in fluid system is called MantaFlow, and it uses a technique called FLIP, which stands for Fluid Implicit Particle. It tracks the fluid as both particles and a background grid at the same time, which is what lets it handle splashing, pouring, and draining in a physically plausible way. As I unfortunately learned through my various experiments, MantaFlow is not that great. Flip Fluids, on the other hand, is a separate add-on for Blender that uses the exact same flip technique, built by a separate team, being a much better and reliable alternative. One of its bigger technical advantages is a much more advanced viscosity solver, something that MantaFlow struggles with. For video games, everything is happening in real time, with dynamic physics responding to whatever the player does. You can't calculate how a player is going to interact with the water before they actually do it. On top of that, the game also has to render out lighting, models, effects all in the same instant. Typically, you want your games to run at 60 frames per second or higher, so every one of those calculations has to happen in a very short time frame. Taking the same approach as VFX artists is just not feasible in this sense, so instead of chasing accuracy, game engines cheat around those calculations. Let's look at Unreal Engine, one that aims for incredibly realistic graphics. Unreal uses a particle system called Niagara to fake fluid behavior. It's not actually solving the real fluid equations at all. Instead, it's just moving thousands of small particles around in a way that looks convincing. This way, it looks pretty good, even though it's technically not physically accurate. This works great for simple bodies of water and things like that. However, you can see that faking the fluid effects can still be very computationally heavy when the situation becomes more complicated. You can see very heavy frame drops when I slosh the water around here. These are just basic Niagara effects, so if I drop a cube in the water, you won't see it float or splash. But these things are possible, however they require some modifications to the Niagara system. The cool thing about the game engine approach to fluid simulations is that there's tons of ways to tackle the issue of creating fluid simulations depending on the specific requirements of the game. Let's look at one of my personal favorite games, Half-Life 2. Now, this game is famous for pushing the medium with its physics, so let's look at its water physics specifically. The water surface itself in Half-Life 2 is just a flat static plane, basically a scrolling texture. It doesn't actually deform when something hits it. There's no real waves or ripple physics happening on that surface at all. So when you see a splash or a wake trail behind a moving object, that's not the water physically reacting to the impact. Instead, it's a pre-made visual effect of particles and wake textures that just gets triggered and layered on top whenever something crosses the water surface. The object floating or bobbing on top isn't being pushed by real fluid pressure either. It's actually a simplified buoyancy calculation, just enough to make it look like it's floating naturally. None of these pieces are simulating real fluid behavior on their own, but put it all together and you get something that's completely convincing to the player, which is all really a game needs to do. Now that I've caught you up on the fluid simulation problem, let's turn back to the VFX side of things. Out of the two, games and VFX, VFX is the one that looks closest to real fluid mechanics. It's not running in real time, so it doesn't have to cut the same corners a game engine does. So, here's the question I actually want to answer. Does Blender, a 3D creation software using the same class of VFX style solver, actually obey the laws of fluid dynamics? Is it close to real Newtonian physics? To find out, I'm going to compare it directly against the real math and see how far apart they actually are. I'm going to run a simple experiment. Imagine we have a cylindrical tank with a radius of 0.5 meters. Let's fill that tank up 2 meters high with water. Now, let's drain the tank through a drain hole with a radius of 5 centimeters and see how long it takes to empty. This is actually a very famous scenario in fluid mechanics. These are the exact parameters I'm going to use to measure how close Blender gets to real Newtonian physics. Here I am in Blender setting up the scenario I just described. I'm using the Flip Fluids add-on for the fluid simulation since the Manta fluids are pretty rough. I built the tank with the described dimensions, added the fluid, which will be water in this case, and created the drain hole. Before I bake this, keep this number in mind, resolution. Right now it's set to 150. In a bit, I'm going to change it to 90 and show you exactly what that does. Since this is going to take a while to bake, let me walk through the actual math behind this while it runs. Okay, let's start with what's given. We have the tank radius, the drain radius, the initial height of the water, the discharge coefficient, and gravity. Now let's identify what we're looking for. Well, I want the time it takes for this tank to drain completely. So, what equation do we use to solve for that? Torricelli's law tells us that the speed of water leaving the drain hole depends on the height of the water above it. The taller the column of water, the more pressure will be pushing down and the faster it exits. That's going to be a good equation to go with based on our givens. But wait a minute. I want to find the time it takes for this to drain. There's no t in this equation, so what am I supposed to do? Well, let's think about what Torricelli's law says. The volume leaving the tank per second is equal to the volume leaving through the drain per second. With this, we can do a volume balance on the tank. The rate the tank loses volume has to equal the rate the water flows out the drain. The tank's area times the rate the height is dropping equals the tank's area times the exit velocity. Now, let's take the area of the tank and move it to the other side. Now I notice that all of these are constants, so let's take all of these and let it be equal to k, just to make this equation easier to digest. Now our goal is to find an equation for height as a function of time. What does this equation look like right now? It's got a differential in there, so we know it's a differential equation. And it looks like I can separate the variables on both sides. So, we have a separable differential equation. Separate the variables. Integrate both sides. And apply the initial condition, that at time 0 the height is the full 2 meters. That gives me an equation for height as a function of time. Setting the height to 0 and solving for time gives me the drain time the real physics predicts. Plugging in our numbers for the tank radius, drain radius, and the 2 meters of water, the answer comes out to around 105 seconds. Now we know how long it will really take for the water to drain, so we can compare that with the Blender result. But, since the Blender result will be a visual of the tank draining, I also want a visual representation of the actual result. So, Let's take this equation we found and build a simple CFD around it in MATLAB so we can compare it visually against the Blender result to really get a visual sense of the difference between the two. Here's a quick breakdown of how the program works. It starts from the same equation, but instead of solving it all at once, it steps forward in time in small increments, 0.1 seconds at a time. At each step, it works out how fast the height is currently dropping, applies that small change, and then moves forward in time. And then when you repeat that a couple thousand times, you get the full drain animated in real time. This stepping approach is actually called the Euler method, one of the simplest numerical techniques there is, but it works well here because the time step is small enough to stay accurate. Now I'm going to measure the height of the water inside the tank every 2 seconds. At 24 frames per second, that means I'm going to be checking the height every 48 frames. This way, I can create a graph to stack the Blender simulation up with the actual results. That way we can measure things like error to get an actual mathematical representation of the difference between the two. Quick side tangent. Remember when I said to keep the resolution value in mind? Now I'm going to change the resolution from 150 to 90 and bake that as well to show you what's changing when the resolution does. Resolution controls how finely Blender divides that simulation space into a grid. At 150, the grid is fine enough to capture details accurately. At 90, each cell in that grid is bigger, and a coarser grid means the pressure solving step has less detail to work with, so small features like the 5 cm drain hole don't get represented accurately, even though the particles themselves are tracking fine. So, here's the comparison. The black dashed line is the exact mathematical answer, and the orange dots are what Blender actually did at resolution 150. If you just compare drain time, Blender looks really good. It drained the tank at 110 seconds. The theoretical answer was around 105. That's under 5% error, which sounds like Blender is basically nailing the physics. But wait, we know that's definitely not right. I mean, when we look at the two side by side, there's a clear discrepancy. Definitely not just 5% error between the two. Look at the graph. We can see that there's a crazy amount of volume loss right at the start. So when I actually compare the two curves point by point, we'll get a much better comparison. If you look 20 seconds in, the real physics says the tank should be about 1.3 meters. Blender says it's already down to 12 centimeters. And then by 30 seconds, the Blender tank is basically empty, while the theoretical curve still has a full meter of water left to drain. So, when I measure the gap across the entire simulation, the error comes out to over 70%. My best guess as to the source of this error is that once the water gets down to just a few centimeters, it's thinner than the single grid in the cell of the simulation, and the solver just can't represent something that thin accurately anymore. Volume loss is actually a well-known issue with flip-style solvers specifically. The method works by constantly shifting information back and forth between particles in a background grid. And when a layer of fluid gets thinner than one grid cell, that handoff starts to break down. So, in conclusion, this experiment highlights why fluid simulation is such a difficult problem in the first place. Something can look completely convincing and still be getting the underlying physics wrong the entire way through. And this was about as simple as the fluid problem can get. One tank, one hole, one direction of flow. Real engineering problems involve turbulence, mixing, multiple fluids interacting, complex geometry, chemical reactions happening inside the flow. Every one of those adds more room for error. If Blender can lose track of the physics on something this basic, that gap only will get wider as the problem gets more complicated. This is exactly why having accurate and powerful fluid simulators are so critical in actual engineering work.